June 8, 2026. Somewhere high above the equatorial Pacific, a satellite is quietly measuring the shape of the sea. It's called Sentinel-6 Michael Freilich. It launched in 2020, built by NASA and led by the European Space Agency, and its whole job is to watch the surface of the ocean from orbit. Every 10 days, it passes over the same stretch of water and measures how high that surface sits, down to a fraction of an inch. On this particular pass, it finds something: a long band of water running along the equator. It stretches for hundreds of miles, and it's sitting more than 6 inches higher than it should be, about 15 centimeters. Now, that doesn't sound like much. A raised strip of ocean, barely taller than the width of your hand, easy to miss. But the sea does not lift itself for no reason. Warm water expands. When the upper ocean heats up, it takes up more room, and the surface rises. So a band of ocean sitting 6 inches too high isn't really a story about height at all. It's a map of hidden heat. And the heat drawn on this map is enormous. 3 days after that image was captured, on the 11th of June, the United States National Oceanic and Atmospheric Administration made it official. After sea surface temperatures in the central and eastern equatorial Pacific had run at least half a degree Celsius above average for months on end, it declared that the warm phase had returned. The most powerful natural climate pattern on Earth had woken up. And almost everyone watching it had the same quiet thought at once. Not this is happening, but this is happening far too fast. But here's the part that reaches your doorstep. That heat is not going to stay out in the Pacific. A warm pool on the equator doesn't just sit there. It rises into the atmosphere, takes hold of the winds that steer weather across entire continents, and drags them out of place, deciding where the rain falls, where the storms track, where the cold pours in, and where it never shows up at all. And this event is forecast to reach its peak late in the year, right as the northern half of the planet turns toward winter. So the real story was never out at sea. It's the season about to arrive at your door, quietly redrawn by 6 inches of water hundreds of miles away that almost nobody would have noticed. To understand why a 6-inch rise in the sea sent a ripple of unease through climate science, you have to understand what the thing under it actually is. The pattern is called the El Niño-Southern oscillation. Most people just call it El Niño. It's a recurring seesaw in the tropical Pacific, and it has 2 faces. El Niño is the warm one. Its sister, La Niña, is the cool one. The ocean swings between them, back and forth, year after year. When El Niño takes over, the tropical Pacific releases a vast store of heat from the ocean into the atmosphere. That temporarily raises the temperature of the entire planet, and it reshapes where rain falls and where storms form all around the world. It is, quite simply, the single largest source of year-to-year change in global temperature. So this is not weather. This is the dial that turns the whole planet's thermostat up or down for a year at a time. And in the middle of 2026, that dial was climbing faster than almost anyone had ever seen. Here's how scientists measure it. Out in the central Pacific, there's a rectangle of ocean they call the Niño 3.4 region. They watch the temperature there, compare it to normal, and that single number tells you which phase you're in and how strong it is. When the water in that region runs more than half a degree Celsius warmer than normal, that's an El Niño. Below half a degree colder, that's a La Niña. For 2 years before all this, the Pacific had been sitting in La Niña, cool, quiet. The start of 2026 was still shaped by its lingering grip. January came in only the 4th or 5th warmest January on record because that fading cool phase was holding temperatures down. And then, in April, the whole thing flipped. The Niño 3.4 index crossed the half-degree line into El Niño territory. In May, it reached a full degree. By June, it had climbed to 1.6 degrees above normal, already strong enough to be classed as a strong event. And in the first few weeks of July, the number shot past 2 degrees. That threshold matters because 2 degrees has a name. When the Pacific sustains warming that high, forecasters stop calling it strong and start calling it very strong. A super El Niño. By early July, the official assessment from the United States Climate Prediction Center had stopped hedging. It reported that a broad area of the central and eastern equatorial Pacific was running more than a degree above normal, that a deep pulse of warmth called a downwelling Kelvin wave had just pushed the boundary between warm and cold water deeper and heated the Eastern Ocean, and that the atmosphere was answering in step. The great pressure seesaw that scientists track alongside the ocean had swung firmly to the El Niño side, and it put a number on what came next. A 97% chance that the event would continue right through the end of the year and into early spring of 2027. Not if anymore. When and how large? There was an even sharper figure buried in that same assessment. It placed the odds of a very strong event through October, November, and December at 81%, an event that, if it arrived, would rank among the largest in the entire historical record, going back to 1950. Watching it happen was a scientist named Séverine Fournier, a sea-level researcher at NASA's Jet Propulsion Laboratory. She's one of the people responsible for reading exactly the kind of satellite data that captured that raised band of ocean, and she is careful with her words. She'll remind you that every one of these events is different, that no two behave the same way, that you cannot simply assume the past will repeat. But even she, choosing her words carefully, looking at the June data, said what a lot of her colleagues were thinking. For now, she said, it looks like it's going to be a big one, more so than she would have said even a week earlier. And then, immediately, the caution again, we still need more observations to know what's going to happen. That tension, right there, is the whole story. Something enormous was clearly building, and the people best equipped to measure it kept reaching for the same 2 words at once: remarkable and uncertain. There's a climate scientist named Zeke Hausfather who describes himself as a measured person, not prone to alarm. He works with these numbers every day, and he's spent years being the calm voice in the room. He says that in recent years there was only one moment that truly shocked him. It was September of 2023, when the global temperature for that month came in a full 0.5 degree Celsius, warmer than any September ever recorded before it. Not a new record by a hair. A new record by a landslide. That, he said, was the one time the data genuinely stunned him. Once. Until the summer of 2026. Because when the July forecasts came in, they showed him something he had no framework for. Now, to see what he saw, you have to know how these forecasts are made. Nobody predicts an El Niño with a single crystal ball. Instead, scientists run enormous ensembles of computer models, the same climate system simulated over and over. Each run started from slightly different conditions, so the spread of the results tells you the range of what's possible. In July of 2026, the forecast pulled together 667 of these individual model runs from 14 different modeling groups around the world. And here is the single most surprising fact in this entire story. The middle of that forecast, the multi-model median for where this El Niño will peak, landed at 3.6 degrees Celsius above normal. Let that sit for a moment. Because to understand what 3.6 means, you need one comparison. The strongest El Niño ever reliably recorded peaked at around 2.75 degrees during the great event of 2015 and 2016. The new forecast wasn't creeping past that old record. It was sitting roughly 0.8 of a degree above it. And that gap is the part that stops you cold. Across a century and a half of observations, the difference between the strongest El Niño ever seen and the 5th strongest is only about 0.5 degree. 5 of the biggest events in recorded history are packed into a band 0.5 degree wide. This forecast was pointing to something 0.8 of a degree beyond the top of that band, outside the entire envelope of anything humans have ever measured. More than 91% of those 667 model runs predicted an event stronger than the 2015 to 2016 record. The middle 80% of the whole ensemble sat at or above that all-time high. Even the low end of the plume grazed it. Every single one of the 14 modeling groups put its own median peak in very strong territory. And all but one of them put that median above the standing record. For a measured man who had been shocked exactly once in recent memory, this was the second time. And it wasn't just one ensemble saying it. A separate experimental prediction system, run at a major American geophysical laboratory and started on the 1st of July, told the same story from a different direction. All 30 of its individual forecast runs produced a peak that was at least competitive with the strongest events of the past century. And every one of them ran warmer than the same system's forecast from the month before. It added a single new detail worth holding on to. After peaking in late fall or early winter, this El Niño was expected to weaken through the winter and into the spring. A giant, but not a permanent one. The rest of the forecasting world had converged to the same place, so there's no need to walk through each one. It's enough to say that when one widely watched group tallied the models, 23 out of 26 agreed a super El Niño was coming by the end of the year. When you get agreement like that across independent systems built by different people in different countries, it stops feeling like a guess. It starts feeling like a measurement of something already underway. So how do you actually build an El Niño this large? What is the physical machinery underneath that rising number? Let's start at the surface. Under normal conditions, steady winds, called the trade winds, blow across the tropical Pacific from east to west. They act like a fan pushing the warm surface water toward the western side of the ocean, piling it up near Indonesia and Australia. On the eastern side, near the Americas, that departing warm water is replaced from below cold. Deep water rises up to take its place. That upward flow is called upwelling, and it's what normally keeps the ocean off the coast of South America cool. El Niño begins when that fan falters, when the trade winds weaken, or briefly reverse and blow from the west instead. The piled-up warm water in the west is suddenly released. It surges back eastward across the ocean in a broad, slow pulse, a wave hundreds of miles wide that barely lifts the surface, but carries a colossal amount of heat beneath it. Scientists call these Kelvin waves, and they travel from west to east across the entire basin over a matter of months. That's exactly what the satellite photographed. That 6-inch band of raised ocean was a Kelvin wave heat in transit, made briefly visible from space. As that warm water arrives in the east, it deepens the warm surface layer and pushes down the boundary between warm and cold water. The cold upwelling below can no longer break through, so the eastern Pacific warms further. And here is where the whole thing turns dangerous, because the ocean and the atmosphere start feeding each other. When the sea surface in the right place climbs past a threshold of around 28 degrees Celsius, the air above it begins to rise violently. Deep towers of storm cloud build. That rising air pulls in more wind from the west, and those westerly winds shove even more warm water eastward, which warms the surface even more, which drives even stronger winds. That loop has a name. It's called the Bjerknes feedback. And once it takes hold, it can spiral the ocean, warming the air pushing the ocean, around and around, each turn amplifying the last. That runaway loop is what separates an ordinary El Niño from the extreme ones. It's the reason a super El Niño is possible at all. In 2026, that loop was already spinning. Convection, the rising storm activity, had strengthened over the central and east-central Pacific, exactly where you'd expect. And over Indonesia, on the other side, it had been suppressed. Rising air here, sinking air there. A textbook signature of the machine switching on. And there was one more piece, hidden below the surface, that made forecasters especially nervous. For most of a year, A deep pool of extraordinarily warm water had been building up beneath the tropical Pacific. Satellites and instruments tracked the temperature in the upper 1,000 feet of the ocean, roughly the top 300 meters, and watched this reservoir grow and intensify through the spring and into summer. In places, parts of that water column ran 7.5 degrees Celsius or more above average. That's the fuel tank. A shallow patch of warm surface water can fizzle out, but a deep, enormous store of heat below the surface can keep feeding a developing El Niño for months. This one was vast. Now, a fair question. If the number was 3.6 degrees, was that real warming from El Niño? Or was some of it just the background heat of a planet that's been warming for decades? Scientists asked exactly that. Because the whole tropical ocean has warmed due to human greenhouse gas emissions, the raw numbers can overstate how strong an event truly is. So they use a cleaner measure that subtracts out the general tropical warming and isolates just the El Niño signal itself. On that stricter measure, the July forecast still pointed to a record. Its median peak came in at 3.1 degrees. The previous record on that scale belonged to the event of 1982 and 1983 at around 2.69 degrees. Even after carefully removing the fingerprint of climate change, more than 3/4 of the model runs still showed a brand new record. Whichever way you measured it, the ocean was saying the same thing. And buried inside all of this was one quiet, easy-to-miss admission from the scientists themselves. No ensemble of models had ever forecast an El Niño this strong and then been able to check itself against reality, because an El Niño this strong had never actually happened. The instruments were pointing somewhere. The instruments had never been tested. It passed almost without comment at the time. Hold on to it. Here's where the picture gets genuinely strange. In the quiet way that the most interesting data always does. Start with the speed. Scientists have daily temperature records for the Niño 3.4 region stretching back 45 years, and in all that time, no year had ever been anywhere near this warm this early. By this point in July, the ocean was already running around 2 degrees Celsius above its adjusted average, already grazing super El Niño strength, months before these events normally reach their peak. Compare that to the two most famous fast-starting El Niños in living memory. In 1997, the previous benchmark for an explosive onset, the index at this same date sat at about 1.6 degrees. In 2015, it was around 1.3. In 2026, it was already at 2. And there was something even odder about how this one began. The 2015 event had a head start. It began its year already warm, primed by a smaller event before it. This one had no such advantage. It launched from genuinely La Niña-ish, cool conditions back in January, and rocketed upward from a standing start. It was developing faster than 1997, from a colder beginning, with further intensification still expected to come. Then there's the shape of the forecast itself, which had been quietly building all spring. If you lined up the model runs month by month, March, April, May, June, July, you saw the same thing in nearly every one. Each new run came in warmer than the last. Across 5 months and 13 independent modeling systems, the forecast kept climbing because the real ocean kept outrunning it. The observed water temperatures kept coming in hotter than the models had dared to predict, forcing them upward again and again. That pattern, a forecast revised warmer over and over as the picture sharpens, is the classic signature of a real, intensifying event, rather than random noise in the models. There's a small, almost human detail hidden in that climb. One model, run by an American research center, had been calling for roughly 4 degrees all the way back in March, when that number looked frankly absurd, and other scientists had said so out loud at the time. By July, the rest of the ensemble had quietly drifted toward it. The outlier had been early, not wrong, and the forecasts weren't all in perfect agreement either. One model kept producing a peak of over 5 degrees, more than a full degree hotter than the next warmest, so extreme that scientists set it aside as an outlier to discount. The point is that even when you throw out the wildest result, the middle of the pack still pointed to a record. The event didn't need the outliers to be historic. It was historic in the median. Now, step back from the models and look at the raw ocean readings from July, because they carry their own quiet oddities. That single El Niño index, most people quote, is really an average across a whole region. Underneath the average, the eastern edge of the Pacific, the strip nearest South America, was running far hotter than the rest, sitting close to 2.7 degrees above normal, while the western edge was barely half a degree up. The heat was piled toward the east, exactly where the feedback loop lives, and this had already touched land months before any of the headline forecasts. The first Kelvin wave of the year, generated back in January, had been strong enough that 2 months later it produced warm water anomalies along the coast of Peru. It arrived so early and so clearly that Peruvian authorities declared a state of alert as early as February over the development of a coastal El Niño. A regional warning, sounded before the global event even had a name. Finally, look north, far from the Pacific, at the ice. The Arctic had spent much of 2026 in record low territory. It began the year with the joint lowest winter maximum of sea ice in the entire satellite record. Across the year so far, daily ice extent had set or tied record lows on 39 separate days, with the most recent falling in early July. At the bottom of the world, Antarctic sea ice was also running well below its historical range, though it had stayed clear of its own record lows. None of these things, the speed, the piled-up eastern heat, the vanishing ice, the models converging on the impossible, was hyped. Each was just quietly logged, but together they described an ocean atmosphere system doing something it had not been observed doing before. So, a record may be forming out in the middle of the ocean. Here's the part that actually reaches your doorstep. But first, a warning about what warm can mean on the ground, because the first half of 2026 had already offered a preview. The opening 6 months of the year came in as the third warmest start to any year on record, around 1.4 degrees Celsius above pre-industrial levels, behind only 2024 and 2025. And it wasn't warm in scattered patches. More than 30% of the entire surface of the planet had a top 5 warmest start to the year. Around 7% had its warmest ever, and not a single grid cell anywhere on Earth recorded a top 5 coldest start. The cold, statistically, had almost stopped happening. Then came the last week of June, and Europe. Western Europe endured its hottest June ever recorded, averaging around 3 degrees Celsius above the recent norm and beating a record that had been set only a year earlier. A dome of hot air parked over the continent from the 22nd to the 30th of June, and under it, records fell in bulk. 10 all-time national heat records and roughly 400 long-standing station records, gone in a little over a week. France set a new June national record of 44.3 degrees Celsius. The United Kingdom broke its own June record on 3 consecutive days, reaching 37.3. And the humid, unrelenting heat carried a human cost estimated in the thousands of lives. A second, separate dome of heat brought its own record June temperatures to parts of North America at nearly the same time. That was the world before the El Niño peaked. That was the warm-up act. Now hold that image and turn toward winter. Because El Niño doesn't stay in the Pacific. When the warmest water shifts east, the zones of towering thunderstorm activity move with it. And when those storm zones move, they tug on the great high-altitude rivers of wind, the jet streams that steer weather across entire continents. A rearrangement out at the equator sends ripples all the way into your local forecast. Start with the coming winter across the United States, because a strong El Niño has a fairly consistent signature there. In these events, the southern branch of the jet stream, the subtropical one, gets, in effect, turbocharged. It carries storm after storm across the bottom of the country. So the southern tier tends to run wetter, from parts of California and the desert southwest, across Texas, all the way to Florida and the southeast. If the air is cold enough when those storms arrive, that extra moisture can fall as snow. Hawaii, too, often sees a rainier stretch before drying out sharply in the year that follows. Now flip to the north, and the pattern reverses. Much of the northern United States tends to run milder and drier in a stronger El Niño, the Northwest, the Northern Rockies, the Northern Plains, the Midwest. Warmth is a hallmark of these winters across the Midwest in particular. In plain terms, for a lot of people in the north, it means the heating bill won't be as steep this year. That's the trade at the heart of the title. A super El Niño doesn't make winter uniformly worse or better. It tilts it, soaking the south and taking the edge off the cold in the north. And this reshaping doesn't stop at one country's borders. The same displacement of rainfall plays out across the whole planet. During El Niño, parts of Africa, India, Australia, the Philippines, Indonesia, the Caribbean, and northern South America tend to trend markedly drier. Meanwhile, the lighter trade winds and warm water set the table for heavier rain in parts of Ecuador and Peru, and wetter than normal conditions across parts of Eastern Africa, Central Asia, Chile, Uruguay, and Paraguay. There's even an effect out at sea in a place you might not expect. A stronger El Niño tends to produce more sinking air and stronger wind shear over parts of the Atlantic conditions that are hostile to hurricanes. So, Atlantic hurricane seasons are often quieter during strong El Niños, which is why major forecasting groups had already trimmed their expected storm counts. On the other side of the continent, the eastern and central Pacific typically grow more active instead. But there's one impact scientists were highly confident about, and it's the largest of all: global temperature. All that heat pouring out of the equatorial Pacific gets released into the atmosphere, and the broad zones of dry, sunlit conditions let the surface bake. The result is a spike in the temperature of the entire planet. The previous Super El Niño helped push 2015 and 2016 to shatter global records years that remain among the 10 warmest ever measured. Given that the year before all this was already the planet's third warmest, a fresh assault on the record books looked, in the words of the forecasters, close to a slam dunk. And here the story splits into two, because of a delay built into the physics. The planet's temperature lags the tropical Pacific by around 3 to 5 months. So an El Niño that peaks in November and December doesn't do its greatest damage to the year it develops in. It does it to the next one. We've watched this exact sequence before, in 1997 and 1998, in 2015 and 2016, in 2023 and 2024. Each time, the year the El Niño developed ran warm, and the following year came in record smashing, which means the biggest climate story of this event may not be 2026 at all. For 2026 itself, the picture was a genuine coin toss with a lean. The central estimate had the year finishing around 1.51 degrees Celsius above pre-industrial levels, most likely the second warmest year ever, just behind the record of 2024 and ahead of 2023 and 2025. The chance of it actually beating the record had climbed steeply through the year, from 7% using March data to 16% in April, 24% in May, 27% in June, and 35% by mid-July. And here's the strange thing about that rising chance. It had almost nothing to do with the temperatures actually recorded in 2026. Those had drifted slightly down over the same stretch. Nearly all of the increase came from one thing and one thing only: the El Niño forecast for late in the year being revised upward again and again. Whether 2026 formally takes the crown may come down to a technicality which temperature record you consult. There are 6 major groups that each keep their own global thermometer for the planet. The ones run out of NASA, out of NOAA, out of the Hadley Centre in Britain, out of Berkeley, out of Europe's Copernicus service, and out of Japan's meteorological agency. They mostly agree. But at the edges, at the exact question of whether one year nudges past another, they can part ways. Run the 2026 projection through each one, and the odds of a new record ranged from around 2 in 3 in the NASA and Berkeley numbers, down to roughly 1 in 3, 1 in 4, and as low as 1 in 10 in the others. The reason for the split is oddly human. It comes down to how exceptional each group thought the previous record year, 2024, actually was. The groups that measured a particularly hot 2024 left 2026 with more ground to make up, and so give it a lower chance. The groups that measured a cooler 2024 have 2026 nudging just ahead. So it's entirely possible that when the final numbers land, different scientific teams, looking at the same planet, will disagree about whether a record was even broken. The headline in January could hinge on nothing more than the dataset you happen to open. But 2027 is a different matter. Carried forward by the lag, the projection for 2027 landed near 1.71 degrees above pre-industrial levels, a figure that would comfortably set a new record for the warmest year in human history, with better than a 9 in 10 chance of doing so. Before we reach the end, there's a deeper reason this particular El Niño matters, and it's about the world it's arriving into. Because the atmosphere it's warming is no longer the atmosphere of the last century, there's a simple, unforgiving piece of physics behind this. Warmer air can hold more water vapor for every degree Fahrenheit of warming. The air's capacity to carry water rises by roughly 4%. As one climate scientist put it, the warmer the air, the thirstier the air. A heating atmosphere becomes a bigger sponge, and a bigger sponge cuts both ways. In wet times, that loaded air wrings out as heavier rain. In dry times, that thirsty air pulls moisture faster out of soil and plants and reservoirs, deepening droughts. The same warming does both in the same places at different moments. The result has a name that captures it perfectly: whiplash. Sudden swings between soaking wet and bone dry, back to back. The clearest example came at the end of 2022. On Christmas Day, most of California sat in serious drought reservoirs critically low, crops failing, water bills climbing. Then, the day after Christmas, it began to rain. Over just 3 weeks, 9 powerful atmospheric rivers, narrow streams of water vapor that ride the wind and dump their load against the mountains, rolled into the coast. That's essentially a whole season's worth of storms in 3 weeks. The flooding and damage led to 22 deaths and economic losses estimated at between $5 and $7 billion. From critically dry to catastrophically wet in a matter of days. Researchers now study those transitions as their own kind of hazard, and one hydrologist described the problem with a metaphor anyone can feel. Managing water, he said, is like keeping a checking account. Inflows are deposits, outflows are withdrawals, and you try to hold a balance. But if these violent swings keep happening, one after another, you find yourself dipping into that account over and over until there's nothing left. And the analyses are consistent. These swings are happening more often than they were a generation ago. One study of 50 years of global data found that these whiplash events were roughly 7.5% more common by 2015 than they had been in 1975, and that the fastest kind swings inside a 3-month window were around 30% more common. A separate look at nearly 500 stream gauges across the western United States found that over 4 decades, 44% of them had recorded at least one dry to wet whiplash within 2 consecutive years, and nearly a quarter had recorded the reverse. In California, swings that used to strike every 3rd or 4th year were now hitting in about half of all years studied, and were projected to keep climbing. The same thirst shows up on farmland, where researchers gave it another name: thirst waves. A thirst wave is a stretch of at least 3 days when the atmosphere's demand for water runs extremely high the sky, in effect, drinking hard from the soil. Across 4 decades of American cropland, the typical thirst wave carried an intensity of around 0.8 of a millimeter a day, lasted about 4 days, and struck close to 3 times a growing season. All 3 of those measures have been climbing. And the share of places that used to escape a growing season without any thirst wave at all has been shrinking steadily. The reprieve is getting rarer. Which brings us to why a super El Niño, specifically, sits at the center of the worry. There's a broader concept that scientists call a climate regime shift, not a passing anomaly, but an abrupt, lasting jump of a whole region from one stable state to another, one that can persist for years and is hard to reverse. And the research suggests that super El Niño events are unusually capable of triggering them. We only have 3 true super El Niños in the observational record: the events of 1982 and 1983, 1997 and 1998, and 2015 and 2016. But each one left fingerprints that outlasted it. After the 1997 event, part of the North Pacific abruptly cooled by around 0.8 of a degree and stayed there. After 2015, the waters of the Gulf of Mexico shifted, in a change that may have fed into the intensification of hurricanes along that coast. Central Australia swung from drought to wet after one super El Niño, then from wet back to dry after the next. And the 2015 event helped drive record heat and extreme drought deep into the eastern Amazon. These aren't temporary weather blips. They're the climate's baseline being shoved into a new position and left there. And the studies indicate that as the planet keeps warming, super El Niños will become even more effective at delivering these shifts. One recent analysis went as far as suggesting the economic toll of a strengthening event like this could run into the trillions of dollars in the years that follow, a figure worth treating with caution, but a measure of how seriously the risk is being weighed. There's one more comparison worth sitting with, because it's the one the scientists kept returning to: 1997. The 1997 event is the benchmark. It happened when satellites and ocean instruments were already good enough to watch it in detail, so it became the yardstick against which every later event is measured. And the heat reserves stored in the tropical Pacific in the first half of 2026 were of the same order of magnitude as those in 1997 at the same point in the year. But the comparison is not clean, and the scientists were the first to say so. The Pacific of 2026 is warmer to begin with. Sea levels are higher, lifted by decades of climate change. Those shifts in the ocean's baseline state could change the very mechanics of how an El Niño develops, and exactly how, no one can yet quantify. By one measure, 2026 had actually produced fewer of those warm Kelvin waves than 1997 had by the same date, even as the overall signal ran hotter. So even the best reference point we have doesn't quite fit. We are comparing this event to the closest thing we've seen, and being told, honestly, that the closest thing we've seen may not be close enough. We have never been better at watching an ocean. Think about what was pointed at this one stretch of the Pacific. A satellite in orbit, timing radar pulses off the sea surface to within a fraction of an inch. Arrays of instruments strung through the water, reading the temperature of a layer 300 meters deep. 667 model runs from 14 groups on multiple continents, all turning at once. Aircraft that fly out over the Pacific every winter to measure the storms before they form. A dedicated center, founded more than a decade ago by a scientist who wanted to see the atmospheric rivers coming before they hit the coast. We built all of it. And through all of it, in the summer of 2026, the same signal kept coming back, sharper each month. The dial was turning. Faster than 1997, hotter than 2015. climbing from a cold start toward a peak that the models placed somewhere no measured event had ever reached 3.6 degrees. 0.8 of a degree past a record that had stood alone at the top for a decade, out beyond a band that holds 5 of the greatest events of the last 150 years. And here is where that quiet admission from earlier comes back around. For all the instruments and all the model runs, no ensemble had ever forecast an El Niño this strong and then been able to check itself against what actually happened, because an event this strong had never happened. The agreement between the models was striking. But agreement is not the same thing as proof. The forecasts were reliable in a world that had been observed. This was pointing outside it. The scientists knew this and said it plainly. The uncertainties could cut both ways. The event might land softer than the median, or harder. But the deepest unease wasn't really about the models at all. It was about the ocean, which wasn't waiting for anyone's forecast. By the middle of July, before the peak season had even arrived, the real water was already running at super El Niño strength, not in a simulation, but in the sea itself. There's a phrase the researchers used for where that left them, and it fits better than anything invented could. The observed ocean, not just the models, was already in uncharted waters. We have spent decades learning to read this pattern: the winds, the waves, the deep pool of hidden heat, the way a shift at the equator can drain a reservoir in California and take the frost off a window in the Midwest and push the warmest year in human history one square closer on the board. We have learned enough to see this one coming while it's still building, to sound the alert in Peru in February, and to argue about the record in the datasets before the year is even out. And it's precisely because we can see it so clearly that we can also see the edge of the map. The place where the record stops, where the models have never been tested, where the water is warmer than any water we have ever measured this early in the year. We built the instruments. We launched the satellite. We moored the buoys and flew the planes and ran the models until they converged. And what all of it told us, in the end, was not an answer. It was that the ocean had already gone somewhere we had never followed it before, and that all our watching could do now was hold its breath and wait to see how far it would go.